couple of minutes before official start time of the class. Does anybody have anything they would like to ask me? Yep. The midterm will be the same as the sample midterm, so that's includes 2 or 3 questions at the end on probability. But from what you know about probability right now, those are questions really about counting. You take the size of one set and divide by the size of another set. So. That's it? No other burning questions? Yeah. Am I going to post the answers for the 2019 midterm? No, I don't think so. I think it's good exercise for you guys to have some that don't have answers. I mean, the answers are almost useless anyway, right? They're just a bunch of letters. If you weren't able to do the question yourself, then being shown the answer doesn't help you. The only thing it helps you with is if you thought you had the right answer, it tells you that and you didn't. It tells you when you were wrong. Yep. You can bring calculators to the exam as long as they're stupid calculators. So not your cell phone, for example. Yeah. There are no office hours during the reading week. So. Yes?
How many questions do we expect for each category?
The distribution will be exactly like on the sample exams. The way I make these things is I take an old exam and I say, oh, question 1 on this exam was about this kind of thing. Let me make a question about this thing. Question 2 was about this. Let me make a question about that. So layout's exactly the same, which is why I know how many probability questions will be, and they will be the last 2 or 3 questions. So, the point is not to surprise you, for example, and take one topic on the course that nobody understands and make the whole exam about that. It's to give you a fair chance to succeed. And so that's why today we're going to go over one of these old exams, and we'll solve the questions on it. Not because it's that useful to solve the questions, but while doing so, we'll also see strategies that you can use when working with a multiple choice exam in combinatorics. So there's things that are quite different when doing an exam than when doing assignments. So for example, if I gave you an assignment with these 17 questions on them without the answers, this would be a long process, even if they were easy questions, just for you to carefully write down all of the answers. Luckily with a multiple choice exam, that's not an issue. As soon as you know the correct answer, you select it and move on. You don't have to justify things, you don't have to prove things, and sometimes you can figure out the correct answer just by the process of eliminating answers that are obviously incorrect. So let's start here. And unlike most of these things, the first question already is a bit tricky. Not because this is a difficult question. I think most of you could do this and get a correct answer. The issue here is, as we saw, when you count something, depending on exactly how you count it, you can get formulas that look different from each other, even though they're all the same. And this is one where that happens. So it says you have n students on the CCSS, and you need to elect a board of directors, which has one very important person who is the president. It has two vice presidents who are indistinguishable from each other, so they don't have separate roles, they're just both vice presidents. And then it has 5 members of an advisory board, which again, they're all indistinguishable, meaning they don't have different roles on the board. So that's just five different people need to be the advisory board, 2 different people need to be the vice presidents, and 1 person needs to be the president, and those should all be 8 different people. So if you read this question, you'll realize that's what it comes to. So without looking at the answers, you would say, okay, so and how many ways are there to make up this advisory board or board of directors out of these n students? So if you didn't look ahead at the answers, then this looks like an easy application of the product rule. And it is. So I need to choose a president. There are n ways to choose the president. I also need to choose 2 vice presidents. Those vice presidents have to be different than the president, so I'm choosing them from a set of size n minus 1, and I'm choosing 2 of them. And then I have to choose 5 members of the, what do they call it, advisory board, and they have to be different from the VPs, and they have to be different from the president, so I'm choosing from a set of size n minus 3, 5 people. So that's a correct answer for this question if it was not a multiple choice question. Just the product rule, choose the president, then choose the 2 vice presidents, then choose the 5 members of the advisory board. Easy application of the product rule. Problem is, none of these answers look like that. And why is that? Well, that's because when you use the product rule for something this simple, there's different orders in which you could have chosen these things, and they give different looking answers. So at this point, you can either then start writing this out longhand and seeing if you can turn it algebraically into one of these 4 answers. And if you're good at that kind of stuff, you may be able to get there. But the other thing to maybe think about is, well, what if I had done the product rule a different way? Could I get one of these answers? So you look at through the answers, and you see actually all of them have n choose 2 in them. Okay. So what's n choose 2? Well, n choose 2 is the way of picking 2 people out of n, and what's size 2 in this problem? That's the vice presidents. So this suggests that maybe when you use the product rule, first step should be choosing the 2 vice presidents. So choose the 2 vice presidents. From a set of size n, you choose 2 people. Okay. Now, what should you choose next? Well, if the next thing you choose is the president, how many options do you have? N minus 2 options for the president. And then if you choose the advisory board, how many options do you have? Or n minus 2. And for the advisory board, at this point, how many options do you have? So this would be n minus 3, choose 5. Is that answer up there? No, the only answer with an n minus 2 in it is this one, but then it suggests that you're choosing the advisory board from a set of size n minus 2, which doesn't make sense because the advisory board should be different than these 2 things. So that answer with the n minus 2 is not right, so we must be doing things in a different order. So let's back up. Choose the 2 vice presidents. Well, now if we're not choosing the president next, the only thing we can do is choose the members of the advisory board. So anybody who's not the president at this point can be a member of the advisory board. N-2, yeah. Anybody who's not a vice president can be a member of the advisory board. And now the last thing to do is to select the president. We've selected 2 vice presidents, 5 people on the advisory board. That means there's still N-7 left who can be the president. And that answer is up there. So it's answer D in this case. So this is actually an example where the multiple choice format makes the question significantly harder than the non-multiple choice format. There you go. Okay. Question 2. You have a set S consisting of 25 elements. X, Y, and Z are 3 distinct elements of S. What is the number of subsets that contain both X and Y but do not contain Z? Is this a hard question? So a subset that contains X and Y but does not contain Z. So those subsets, how do you generate them? Well, you have to put X and Y in them. And then you pick some other stuff, but you're not allowed to put Z in there. So this other stuff that you pick, where does it come from? It comes from S, but you take away X, Y, and Z. How big is this set? S has size 25. This is a set of size 3. All 3 elements are in S, so I take those out of S. That means this thing, size of this thing, is 22. So if I want to make a set that contains X and Y, but not Z, and it's a subset of this thing, that means I'm just picking any subset of these guys. So I have a subset here of these 22 things. Take any subset of them, add in X and Y, and I'll get a subset that meets all the requirements. How many subsets are there of a set of size 22? 2 to the power 22. And that was one of the first applications of the product rule. Actually, the bijection rule is how we first saw it, but just think of listing out these 22 elements, and for each one you decide whether it's going to be in the subset or whether it's not going to be in the subset. Yep. No, because the set has to include X and Y, so that's just given. They all include that. Can include Z. So all that's left to remain is, all that remains to choose is which of the 22 other elements are going to be in the set. And so, so in this case, there's 2 to the 22 options for those, the rest of the set, other than X and Y. Okay, so that's C in that case. A is a set of 6 elements. B is a set of 13 elements. How many one-to-one functions f from A to B are there? So we saw a formula for that, but maybe it's just easier to work it out from first principles because it's easy to forget these formulas. So what's the size of A again? 6 elements. 1, 2, 3, 4, 5, 6. Over here we have B, and the size of B is 13. And I want a one-to-one function. That means I don't want 2 elements in A mapping to the same element in B. So if I want to define a one-to-one function, I take the first element in A, and I choose what it's going to map to in B. How many options are there? 13. So there were 13 options for that first choice. And the next one, how many options are there for the second element in A? Only 12, because it's not allowed to map to the same thing as the first one. So there's 12 options there. For this one, it has to avoid the 2 that were chosen by the first 2. So that's 11, 10, 9, 8. And there's a formula in the textbook for when A has size n and B has size m, the number of these things, and it's a ratio of factorials, right? So in this case, it would be 13 factorial divided by 7 factorial. So hopefully that's on there. 8, 9, 10, 11, 12, and 13. And indeed, that's answer D in this question. So I feel like I'm moving a little bit fast now. Anybody want to pause? Ask me anything? Yep. For some questions, there'll be actual numbers like this one, and for others, there'll be n's and m's. Okay. Let Sn be the number of bit strings of length n in which the first bit is not equal to the last bit. And then which of the following is true? And you get a bunch of formulas, or candidate formulas for Sn, and you need to figure out which one is correct. So for that, I guess you can, the natural approach to this is the product rule. So, and the natural thing to do to make a bit string of length n, which has special requirements on the first and last bit, is to choose the first and last bits, and then choose the rest of the bits. So I've got this, trying to make this string of length n. There's some special conditions on the first bit and the last bit. Let's focus on those. What are the options for these 2 bits? Yeah? Yeah. So I can put a 1 here and a 0 here, because they're not allowed to both be the same. Or I can put a 0 here and a 1 here. So you choose for the first and last bit, there are 2 different options. Even though in general there would be 4 options for 2 bits, in this case, since they have to be different, as soon as you choose the first one, that determines the other one. Okay. All right, so that's the first step in the procedure that we're going to use in the product rule. The second step is to set all of these bits. How many of them are there? There's n minus 2 of them, and there's no restrictions on these bits. There's no special conditions. So I put any sequence of n minus 2 bits there, and that's the most basic application of the product rule, is that there's 2 to the n minus 2 bit strings of length n minus 2. So we get 2 times 2 to the n minus 2. You look up, oh, I don't immediately see that answer there. But of course, this simplifies. 2 times 2 to the n minus 2 is 2 to the n minus 1. And lots of ways to think about that. So this is one way to think about it. The other is, I write down a bit string of length n minus 1, the first n minus 1 bits, and then the last one I don't have any choice. It has to be different from the first one. So I can write down any bit string of length n minus 1 here, but the last one I don't get to choose. And again, I haven't mentioned it much, but for these questions 3 and 4, even if you didn't know immediately how to tackle them, just browsing through the possible answers already suggests some ways, right? Like question 3, if you didn't remember how we do one-to-one functions, all of the answers have this sort of factorial, partial factorial form, and that should remind you. And they all have 13 in them, so hopefully that reminds you of how you get to there. These ones have a bit more trickiness in them because you may be tempted to think you need something more sophisticated than you do. So start with the simplest approaches first. In this case, the product rule works fine. Okay, now we're looking at strings of length 99. The alphabet is 3 letters, A, B, and C. And how many such strings are there that start with ABC or end with BBB? So, look ahead at the answers. What do you see? You see some that have sum, so they're adding two things together. Some that have a difference. There's a subtraction in there. And so you have to think, if I'm just adding two things together, that looks like the sum rule. And when do you get to use the sum rule? Not cases, but what's special about when you want to know the size of a set that's the union of two sets? When do you get to use the sum rule? Yeah. Yeah. So when S is the union of A and B, then the size of S is equal to the size of A plus the size of B if they're disjoint. So here, S is strings that start with A, B, C, or end with, what are they supposed to end with? B, B, B. So then it's very natural to say A is the strings that start with ABC. B is strings that end with BBB. And indeed, then S is equal to A union B. But are A and B disjoint?
No.
No. There are strings that, because the strings have length 99, there are strings that start with ABC, have a bunch of other stuff in the middle, 93 other characters in the middle, and then they end with BBB. So there's a third set, which is A intersect B, and these are strings that start with ABC and end with BBB. So, how many strings are there? 99, they have like 99, they start with ABC and they use the alphabet ABC. So, first 3 characters are fixed, and then you have to pick 96 other characters. So how many of those are there? So, size of A is 3 to the power 96. Because for each of the characters, starting with the 4th one, you have 3 options for what you put there. How about the size of B? B is strings that end with BBB, but every other character is available. So again, we're in this dichotomy where some of you have no idea what to say, and some of you think this is too trivial to answer. So if you think it's too trivial to answer, answer. Yep.
What is the same size?
The same size as this one. What's the size of B? It's 3 to the 96. Right? Because the strings in B have 96 characters followed by 3 Bs. And those 96 characters can be anything. What about A intersect B? What's the size of that? So these are strings that start with ABC, then there's 93 characters, And then there's BBB. Yep.
B to the power of 93?
Yep. And now when we have S written as the union of A and B, we know how to compute the size of that. It's not by the sum rule, it's by the principle of inclusion-exclusion. So yeah, it starts out like the sum rule. You take the size of A, take the size of B, but you have to subtract the stuff that you've double counted because it was both in A and B. And so you get 2 times 3 to the 96 minus 3 to the 93. And here for this one, looking ahead at the answers, you had to convince yourself that A is not correct because the sum rule does not apply, because the two subsets that you're looking at are not disjoint. Yep.
I have a question. Some rules we use pairwise disjoint.
Yeah.
Pairwise.
What is pairwise?
Yeah.
Pairwise just means for every, so in this case, there's only one pair, A and B, but the sum rule lets you work when you have S is the union of A1, A2, A3, A4, A5, A6, A(n). And pairwise disjoint means if I take AI and AJ, when I is not equal to J, that they have nothing in common. That's true for every I and J.
Pairwise disjoint.
This is pairwise disjoint. No, this is not pairwise disjoint. There is only one pair here, and those things are not disjoint. They're not disjoint because there are strings that start with ABC and end with BBB. Okay. Here's one of these word questions. So there's a sum there, and it's the sum as k goes from 1 to m of m choose k. And it says, what does this count? So the options are the number of non-empty subsets of a set of size m, the number of subsets of a set of size m, the number of bit strings of length m having exactly k many ones, or none of the above. So let's start with option A. The number of non-empty subsets of a set of size m. Is that correct? Let's vote on it. Maybe the majority can be correct. Who thinks that's the correct answer? And who thinks it's not the correct answer? Okay. So the majority seems to think it's correct. Actually, the majority has no opinion or is afraid to express their opinion. But let's think about it. The number of non-empty subsets of a set of size m. If you're non-empty subset, that means your size is 1, or your size is 2, or its size is 3, or your size is 4, or your size, and so on, up to size m. So what is this thing? This sum is counting how many subsets are there of an m-element set of size 1, plus the number of subsets of an m-element set of size 2, plus the number of subsets of an m-element set of size 3. So indeed, that seems to count every non-empty subset. Because k starts at 1 in this sum and not at 0, this counts, I mean, if k started at 0, the answer would be, this counts the number of subsets of a set of size m. In this case, k is starting at 1, so it's counting everything except for the empty subset. Yep. Yeah. So it counts all of the total number of subsets of a set of size m except for the empty ones, which is one empty one actually. Okay, in the city of short last name, every person has a last name with 2 characters. First one is an uppercase letter, second one is a lowercase letter. And what is the minimum number of people needed so that we can guarantee that at least 4 of them have the same last name? So, before we answer it, what kind of question is this? Yeah. Yeah. So we've only seen one way to tackle these kinds of questions, where what's the minimum number of things that you need in order to force some situation. And in this case, the situation that we're trying to force is to have 4 people having the same last name. Okay. So that means we're going to take a bunch of people and shove them into holes where the hole that someone goes into is their last name. So that means we need to know how many holes are there. How many last names are there? A last name is one letter and then followed by another letter. Yep. Yeah. So we're using the pigeonhole principle, and the holes are last names. And a last name is just 2 characters. So that means there are 26 squared holes. All right. Now, I want to force you into a situation where there's at least 4 people with the same last name. So how many people do I need for that? Yep.
3 sets of complete list of organizations.
Yeah. So if I have 3 times 26 squared people, then does that force me to have 4 with the same last name? No, because each last name could be used by exactly 3 people. But if I just take 1 more, then I can't have each last name being used by exactly 3 people, because if each last name is used by exactly 3 people, that means there's only this many people. But I have more than that. And if you remember, the pigeonhole principle said, if you put n pigeons into k holes, so this is our holes, this is the number of pigeons, then you will get 1 hole that contains at least the ceiling of n over k pigeons. And in this case, this number, without the ceiling, this is 3 point something, something positive. It's bigger than 3, right? Because already just this, 3 times 26 squared over 26 squared, that's equal to 3, but it's bigger than that. And so, so this is something that's bigger than 3 inside. We take the ceiling, so we get 4. So this is the right number of, the minimum number of people you need to force that situation. Yeah?
I multiply it by 3 and I add it by 1.
Well, because I was aiming for, I need to have a number of people so that the number of people divided by the number of holes is bigger than 3. So the number of people divided by the number of last names is bigger than 3. What's the smallest number of such people? Well, that's 3 times the number of last names plus 1 more.
Oh, okay, I get it now. Because at least 4, that's why.
Yeah, because you're aiming for at least 4, and as soon as you have slightly more than 3 on average, then you get at least 1 with 4.
That's the one we get slightly more.
Yeah. The nice thing about working with integers is you get this benefit of taking the ceiling. Okay. What's the coefficient of x to the 81, y to the 7 in the expansion of 3x minus 17y to the 88? So what kind of question is this? This is Newton's binomial theorem, and in case you forgot it, there is Newton's binomial theorem on the first page of the exam. So it says that it's You have to do n choose k and times n minus k y to the k. So let's see what we get for this question. Okay, so 3x minus 17y to the 88. That's the formula that we're looking at. 3x plus minus 17y to the 88. And the coefficient we're looking for is x to the 81, y to the 7. So that, in Newton's language, is going to give us 88, choose 7. 3x to the 81 minus 17y to the 7. Pull things out. 88, choose 7. 3 to the 81. 17 to the 7, but this stays negative. And x to the 81, y to the 7. So is that up there as a possible answer? 88 choose 7, 3 to the 81, 17 to the 7, all negated, so it's answer B. So the only sort of tricky bit here is Newton is written in terms of x plus y to the n. Here, x is really 3x and y is really minus 17y. So you just need to introduce auxiliary variables if you like. Okay, how many solutions are there to the equation x1 plus x2 plus x3 plus x4 equals 55, where all of the xi's are bigger than or equal to 0, and they're all integers? And then you see a bunch of options, which all look very simple. They're all simple binomial coefficients. So have we seen how to tackle these things? If you did the assignment, you've done it, and we did it in class. And the hard part now is remembering exactly what the formula was, because there's like a k minus 1 or not, can't remember which. So best to just go back to first principles so you don't make a mistake. All right, we're trying to get 4 numbers, and they should add up to 55. So if I take let's see, 58 buckets, and I place 3 things in those buckets. Maybe not 58. Sorry, that should be, oh yeah, 58. And I place 3 things in those buckets. Then there's some number of empty buckets before the first thing. Call that x1. Some number of empty buckets between these two. Call that x2. Some number here. Call that x3. And some number trailing the last one. Call that x4. What do x1, x2, x3, and x4 add up to? Well, they add up to 58 minus 3 is 55. So from these 58 buckets, if any way that I choose 3 of them, that defines 4 values, x1, x2, x3, x4, that satisfy the conditions I'm looking for. And if I choose 3 different ones, each time I take a different triple of buckets, I get different values for these numbers. So that says that it should be 58, choose 3. And that is on there as option A. Yep.
This was a situation where, let's say, x1 plus x2 plus x3 plus x4 was, it's like greater than or less than 55. Then
Yep.
you would add a 5th variable, and then it would be 59.
Yes. If you have an inequality, so you want them to be at most 55, then you place 4 things in the buckets, and that position of the last thing basically tells you what the sum is. Because if you don't place that last thing at the very end, then you'll get a sum that's smaller than 55. Or another way to do that is you think of this then becomes a 5-variable problem where the 5th variable is x5, and the constraint is that x1, x2, x3, x4, and x5 have to add up exactly to 55, which means that x1, x2, x3, x4 add up to at most 55. Yep.
We do like x1 is bigger than 1, and the rest is like bigger than 0. How is that going to work?
So that's if it's just that x1 is bigger than, has to be bigger than or equal to 1, and the rest of the problem doesn't change, well, that just means that you're picking 3 things from this set here, so not this thing. So then it would be 57, choose 3.
It also would be like bigger than greater than 1.
If all of them are greater than or equal to 1, that's a thing that we've done, shows up on an assignment question. And so there, again, there's a few ways to do it. The one easy way to see it is you can just introduce auxiliary variables and say y1 is equal to x1 minus 1. y2 is equal to x2 minus 1, and so on. And now, if you give me values of x1, x2, and so on that satisfy your thing, that they should all be bigger than or equal to 1, then the y's are values that are all bigger than or equal to 0. And so you see, you can translate it into the case where they should all be bigger than or equal to 0. Yep.
For that drawing, how did you get 58 and then those 3 buckets? I just used a formula.
Well, you can just, hopefully you remember something about this proof that, yeah, you took the number of buckets that you used was the target value 55 plus something, and it was either plus 3 or plus 4. I remember that it's plus 3 in this case, but if you tried plus 4, you'd realize that it doesn't quite make sense. So just try and reconstruct the argument, and if you get it wrong, then you'll realize, oh yeah, it was supposed to be plus 3, and I only picked 3 things, not plus 4, and I picked 4 things.
Okay, can I just use the formula still?
Sure. Yep.
Where your restriction is greater than or equal to 1 and you shift or remove the auxiliary variable, would you still set it equal to 55?
No, because then the y's should add up only to 51, I guess. Right, if all the x's add up to 55, then the y's have to add up to 55 minus 4, because each y is the x minus 1. So you convert it to the original type of problem, but the target value changes, and but that's all that really changes. So you get something like 51 plus 3, so that's 54, choose 3. Yeah.
So like another way to think of it is like when x1 is greater than like a, for example, those A's are fixed, so you can just remove them from the total.
Yeah. Yeah. Okay, recurrence question. Function f from integers onto integers defined by the value at 0 is 7, and the value at n is f of n minus 1 plus 10n minus 6. Okay, so how are we going to tackle this one? Well, the nice thing about these is F0 we know, F1 should be easy to compute, F2 and F3 maybe, and then we can just check if these formulas work. Hopefully all but one of these formulas breaks for a small value of n. So let's just figure out the first couple of values of f. So f of n for big n's is fn minus 1, 10n minus 6. So f of 0 is 7, but f of 1 is 7 plus 10 minus 6 is 11, right? F of n minus 1, 10n minus 6. F of 2 should be 11 plus 20 minus 6. That's 31 minus 6, 25. Stop me if I make a mistake, or if you think that I made a mistake. 25 plus 30 minus 6. 25 and 30 is 55 minus 6 is 49. So now we have a few values of, we know F1, F2, F3. We can start checking these things against these formulas here. All right, so how about that first formula, A? Could it possibly be correct? No, because 4 times 1 squared minus 2 times 1 plus 7. So what do we got? 4 minus 2 is 2 plus 7 equals 9. And that's not equal to f of 1. So A is out. How about B? 4n squared minus n plus 7. Let's check it. Let's check it for 1. 4 times 1 squared minus n is a minus 1 plus 7. That should be 10, right? Yeah? No. That's 10, yeah. That's 10, and that's not equal to f of 1 because f of 1 is 11. So that's B ruled out. C, 5n squared minus 2n plus 7. Is that one quick to rule out? So for f of 1, that's 5 minus 2 is 3 plus 7 is still 10, so that's ruled out because it still fails the f of 1 case. And then finally, the last one is D, 5n squared minus n plus 7. Let's check it for f of 1, but it should be the only one that works. So 5 times 1 squared minus 1 plus 7 is equal to 7 plus 4 is 11. That equals f of 1. That's not a proof at all that that's the correct answer. On the other hand, every other answer is already incorrect for f of 1. So in a multiple choice exam, you can stop here. In a real thing, you would say this is a plausible choice. Let's check it for F2, F3. And if those hold up, let's do an inductive proof that that's the correct answer. But you don't have to do all that in this case. Yeah.
Since our given choices are quadratic, would it maybe be faster if we constructed a table of differences and like generated the coefficients?
Maybe. Since they're quadratic, you can fit them already by having 3 points. So F0, F1, F2 would actually define the whole equation. But that's if you like algebra. All right. The number of bit strings of length n that contain the substring 0000. It looks like you're trying to figure out how many of those there are, and all the possible answers are written in terms of recurrence relations. And 3 of them look kind of similar, and then there's one that sort of stands out. And it stands out because it has a 2 to the, well, it has this extra 2 to the something in it. So let's think about how we would write down such a bit string of length n that contains 4 zeros in a row. So a bit string like that can start with a 1. And then what comes after the 1? Well, it's a bit string of length n minus 1. Is there anything special about that bit string? It has to contain 4 zeros. So the number of things that I can put in here is going to be s of n minus 1 because I still need to make a string that contains 4 zeros. If your string doesn't start with a 1, it could start with a 0, 1. And what comes after that is n minus 2 bits, and they better have 4 zeros in a row somewhere in them because I need 4 zeros in my string. And if it doesn't start with a 0, 1, maybe it starts with a 0, 0, 1, followed by n minus 3 bits, and again, they had better have, somewhere in there, you better find 4 zeros in a row. So the number of bit strings of length n minus 3 that have 4 zeros in a row is by definition s of n minus 3. Or you start with 3 zeros in a 1, followed by n minus 4 bits. And what can those bits be? Well, they have to have 4 zeros in a row. So the number of ways of doing that is, by definition, s of n minus 4. Or, finally, you can start with 4 zeros in a row. What comes after that is n minus 4 bits. Anything special about these bits? I can put anything here now. Because whatever I put here, when I prepend 4 zeros, I'm going to get a string that has 4 zeros in a row in it. So here, I can put 2 to the n minus 4. So that says that, these are mutually exclusive cases. So that says that s of n is s of n minus 1 plus s of n minus 2 plus s of n minus 3 plus s of n minus 4 plus 2 to the n minus 4. And that's all the ways that I can make one of these strings. Is that clear? Yep.
For when you're adding the zeros in front of the one, you also have to count it if some of them are ones?
No, because I can, imagine any bit string, count the number of zeros that it starts with. So that's going to be an integer which is bigger than or equal to 0, right? So if it's equal to 0, this is what the string looks like. It starts with a 1. If it's equal to 1, it starts with a 0, 1. And if it's equal to 2, it starts with 0, 0. If it's equal to 3, it starts with this. And if it's greater than or equal to 4, that means it starts with this. Okay? And so this thing captures all of the rest of the ones. Any string that starts with 4 or more zeros will be counted in this set. Yep.
But let's say you're doing the recursion, and you're constantly doing it, and let's say you never find. So it's like you're constantly looking for that 0, 0, 0, 0, and it basically never stops until you find that 0, 0, 0, 0. So the total length is just arbitrary.
No, I mean this is counting strings of length n. The funny thing that sometimes happens here is some of these things, when n is small, some of these values are 0. Like, well, for example, if n is 3, then the whole thing is 0 because you can't have 4 zeros in a row if your string is only of length 3. But if n is 5, then yeah, you can start with a 1 and then have 4 zeros, but you can't start with a 0, 1 because then you'll never get your 4 zeros and so on. So you're always counting strings of length n. The only thing that's maybe a little bit weird is around the small cases for n less than 8, I guess, these things behave a little bit strangely. N is bigger than or equal to 1. I would like to write the value n as a sum of 1s and 2s. The order in which the things matter, so 1 plus 2 is not the same as 2 plus 1. And you're not allowed to have 2 consecutive 2s. So if well, in any case, and you're not allowed to have 2 consecutive 2s. So the number of ways of doing this is governed by some kind of recurrence. And we saw that in the case where there wasn't this extra rule about 2 consecutive 2s, we saw that that recurrence was, well, however I write the value n, it either starts with a 1 followed by something that sums up to n minus 1, or it starts with a 2 followed by something that sums up to n minus 2, and you get the Fibonacci recurrence this way. S of n is equal to S of n minus 1 plus S of n minus 2. But now we have some additional restriction here, so we have to play that out and see where it goes. So if I want to write n as a sum of 1s and 2s, there's basically 2 options. I can start with a 1, and then what can I put here? Anything that adds up to n minus 1 and doesn't contain 2 2s in a row, right? So that's the thing we're trying to count. So that's the thing that we're calling, you put a 1 and then you have the rest of the thing. This adds up to n minus 1 and should never have 2 2s in a row. Or your string starts with a 2, and then what? Yep.
The next one has to be a 1.
Yeah, so the next one, if it starts with a 2, I'm not allowed to have 2 2s in a row, so the next thing has to be a 1. So we might as well fix that now, and then say, well, what happens to the rest of it? Well, this must then add up to n minus 3, and it should also have not two 2's in a row, so that gives me s of n minus 3. So then I get s of n is equal to s of n minus 1 plus s of n minus 3. Okay. Now, is it clear why I did this step of making sure that this 1 was here? Because if I start with a 2 and then take something here which adds up to n minus 2 and doesn't have two 2's in a row, that doesn't work because this thing here could have started with a 2, right? Could look like that. So this is a string that we're counting in s of n minus 2, but I can't stick a 2 on the front of it because this one starts with 2. So you have to really take this extra step of saying, okay, if I have a 2 here, the next thing has to be a 1, and that means I can put anything I want here as long as it doesn't have two 2's in a row. Because here? Well, because already the thing that I'm writing adds up to 3 at this point, and I need to write the rest of it, so the rest of it has to add up to n minus 3. You have an algorithm here called fib. It takes an integer n bigger than or equal to 0 and looks like it computes the nth Fibonacci number. And when I run fib 55, how many calls are there to fib 50? Well, the easiest way to do that is just to start drawing the recursion tree. So if I call fib 55, and actually this is a good one because it will teach you a lesson about algorithms as well, and why the recursive algorithm for Fibonacci is not efficient and why it's so easy to make it much more efficient. If I call fib 55, well, 55 is not equal to 0 and it's not equal to 1, so it's going to call fib of 54, and it's going to call fib of 53, right? N minus 1, n minus 2. So let's go, and we're interested in the number of calls to fib 50. Let's go here. 54 is going to call 53 and 52. 53 is going to call 52 and 51. 52 is going to call 51 and 50. And 51 is going to call 50 and 49. All right, this is the first time interesting things start happening, and it's actually the only time. So I'm trying to figure out how many times fib of 50 gets called. Here's one of them. Okay? Now, there's still some recursion that happens under here. Will the value 50 ever show up under here? No. Because now it's going to be 49 and 48, and they only go down as you go down this tree. So down here, we're done counting. Is the value 50 ever going to show up over on this side below this? No, it's all going to be values smaller than 49. So now I know what the answer is for 51, right? If you call fib of 50, then it gets called exactly once. Down here, exactly how many times does 50 show up? It's exactly once. It's right here, and then never again. All right. Down here, how many times does 50 show up? I know the answer already. It's written down over here. It's exactly once. So for 52, there will be one call to fib 50 over on this side, shows up here, and another one over on this side that shows up here. So for 52, the answer is 2. This one plus this one. Now, over here for 51, how many times does it show? Does it call fib of 50? I know the answer. It's written down over here already. Figured this out already. So for 53, the answer is whatever you get for 52 plus whatever you get for 51. It's 3. For 52, oh look, I already know the answer. And so that means that for 54, it's going to be 3 plus 2 is 5. For 53, I already know the answer. It's 3. So for 55, it's going to be 5 plus 3 is 8. Look at that, it's a Fibonacci number also. The answer is 8. You can figure it out by doing this recursion tree, but you definitely don't want to do this recursion tree 5 levels deep, because then it has 32 nodes. That's a bit more work than you want to do. You just notice that the same numbers show up all over the place, so once you've figured them out once, you figured them out forever. So the answer is 8. This is also the reason why this is not an efficient algorithm for computing the nth Fibonacci number, because when you want to compute Fibonacci of 55, you end up computing Fibonacci of 52 twice. And you end up computing Fibonacci of 50 8 times. And so the thing just blows up. Insane. All right, here's a question about Justin Bieber. So it takes an integer n, which is a power of 2. This is important for simplifying things. Power of 2 means it's n is equal to 2 to the k for some integer k. And what does Justin Bieber do? If n equals 1, he orders chicken wings. And if n equals 2, he drinks a pint of IPA. And otherwise, he prints, I don't like Justin Bieber, and calls Justin Bieber n over 2. All right? And the question is, for n a power of 2, Bn is the number of times you print, I don't like Justin Bieber. How many times does this get printed? So let's try it. Let's take, for example, n equals 8. Why 8? Because 8 is equal to 2 to the 3, or if you like, the log base 2 of 8 is equal to 3. So if I call this thing with n equals 8, what happens? 8 is not equal to 1, 8 is not equal to 2, and therefore we're in the third case where it prints, I don't like Justin Bieber, and then calls itself recursively with the value 4. 4 is not equal to 1, and it's not equal to 2, so it prints, I don't like Justin Bieber, and calls it recursively, self-recursively with the value of 2. At 2, something different happens. It prints, I don't know, drink, or it doesn't print, it just drinks. And then it's over. Right? So that's what happens when you call this algorithm with n is equal to 8. It prints, I don't like Justin Bieber twice. And if you look at the options, log of 8 is 3, and it prints this thing twice. So it looks like it should be one of these two answers, log of n minus 1, log of n minus 1. And we just need to figure out whether this is true for all n bigger than or equal to 2, or whether it's true for all n bigger than or equal to 1. Yep. The indentation is strange in this one, but I don't think there's an error. Just the indentation looks strange. Yeah, I mean, that final else statement is supposed to be if it's not equal to 1 and it's not equal to 2. Okay, so do we agree that the answer is log n minus 1 for some values of n? Okay, and then it's a question of whether that's true for all n bigger than or equal to 2, or all n bigger than or equal to 1. But if n is equal to 1, then log n is equal to 0. So log n minus 1 is equal to negative 1. So if I give this thing the argument 1, does it print I don't like Justin Bieber negative 1 times? No, it doesn't. The number of times you print something is a natural number, 0, greater than or equal to 0. It's certainly not a negative number. So this can only be true for n bigger than or equal to 2. And indeed, when n is equal to 2, the limiting case, log n is 1, and 1 minus 1, it prints I don't like Justin Bieber 0 times. Yeah. Because I picked the value of n, which was 8, looked at log n, which is 3, ran the algorithm, and saw that it printed it twice. And if you wanted to, you could pick, put another one on top, pick n equals 16. You'll see that it prints it exactly one more time, and then it executes exactly the same way. How did I know that it was? Because the question states that n is a power of 2. Okay. You flip a fair coin 7 times. Define the event. The result of the first flip is equal to the result of the 7th flip. If you know nothing about probability, what do you guess the answer is? I flip a coin now, and then I go do something else for the time it takes me to flip 5 coins, and then I flip it again, which is the 7th flip. What do you think the chances are that those 2 flips are equal? Quarter or no? Half. Right? First coin is either tails, and in which case the second time I flip, I have probability a half of getting tails, or the first coin is heads, in which case the second time I flip, I have probability half of getting heads. So if you know nothing about probability, you say a half. And you pick that answer, and if you're out of time, then that's what you should do. If you don't trust yourself, because probability is full of counterintuitive things, you have to do some counting. So flipping coins several times is a uniform probability space. So that means the possible outcomes of flipping a coin 7 times, it's heads or tails each time. So it's a sequence of, let's say, H's and T's of length 7. So the number of those things is 2 to the 7. And the event A is the set of those sequences that look like this. They start with the heads, and then 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 things, and then a heads, or they have a tails, 2, 3, 4, 5 things, and a tails. These are the sort of outcomes we're interested in, right? Heads, then I don't care what happens, and then heads, or tails, and then I don't care what happens, and then tails. How big is this set? How many things are there that have heads? Then five whatever, 5 characters, H or T, and then heads. Number of these is 2 to the 5. That's the product rule, 2 choices for each of these. And similarly, the number of these is 2 to the 5. So that means the size of A is going to be 2 times 2 to the 5, which is 2 to the 6. So A is the event we're interested in knowing the probability of. S is the total, is the set of all possible outcomes. And this is a uniform probability space. So the probability of A is equal to the size of A over the size of S is equal to 2 to the 6 divided by 2 to the 7 is equal to 1/2. No surprise there at all. But if you know nothing about probability, which you almost, you know nothing more sophisticated about probability than what you know so far, this is the way you have to do this kind of question. Two to the 6, that's 2 to the 5 plus 2 to the 5. Where does 2 to the 5 come from? Here I'm counting sequences where the first thing in the sequence is equal to the last thing in the sequence. In fact, I think we did that even on an earlier question. Yeah. Yep. For now, I would like you to think about these things in the simplest terms possible. In this case, this is it, right? This is how many possible outcomes there are. They're all equally likely. This is how many outcomes there are in the event we're interested in. And therefore, the probability of that event is just the size of the event divided by the size of the sample space. All right, you roll a fair 6-sided die twice. You have 2 events. One of them is the sum of the 2 rolls is 7, and the other one is the result of the first roll is 3. Which of the following is true? Probability of A is equal to the probability of B, probability of A is less than the probability of B, probability of A is bigger than the probability of B. Why don't we just compute the probability of A and probability of B, then we'll know the answer. Anybody remember the probability of A? Yeah. Right. A. So in this space of rolling 2 dice, you have an outcome set which has size 6 squared, 6 choices for the first one, 6 choices for the second one. The event A contains exactly these outcomes, 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1, and probability of A is just equal to the size of A over the size of S. This is a set with 6 elements. So this is 6 over 6 squared is 1 over 6. And let's look at B. B is the event that the result of the first roll is a 3. We explicitly write out B. That means first roll is a 3, second one is a 1, or the first roll is a 3, second one is a 2, or the first roll is a 3, second one is a 3, first one is a 3, second one is a 4, 3, 5, 3, 6. That's B. What's the size of B? Oh, look, it's also equal to 6. And therefore, probability of B is also 1 over 6. So the answer is the probability of A equals the probability of B. The 1 over 6 is kind of obvious, or feels kind of obvious as the probability of B, but if you want to be pedantic about it, this is what you do. You write out all the outcomes where the first one is a 3. There's 6 of them. 6 out of the 36 possible outcomes. Choose a uniformly random 3-element subset from a 7-element set X. What is the probability that 4 is in your set? So, how do we answer this? The question already tells you the size of the sample space. We're choosing 3 elements from a set of size 7. So the size of S for this last one is 7 choose 3. And A is the event that 4 is one of those 3 elements that I chose. So how many subsets of size 3 are there of 1 to 7 that include 4? Well, that means that really every such subset is a subset of size 2 from the set 1, 2, 3, 5, 6, 7. Right? And a subset in here is going to be 4 plus 2 elements of 1, 2, 3, 5, 6, 7. That's what a subset of size 3 that includes 4 looks like. And the number of these things is 6 choose 2. And there's only one of these things. So A is 6 choose. Size of A is 6 choose 2. And therefore the probability of A is equal to 6 choose 2 over 7 choose 3. Now, it would be too easy if that showed up this way. So now we have to beat this up a little bit. What is 6 choose 2? 6 choose 2 is 6 times 5 divided by 2. What is 7 choose 3? 7 choose 3 is 7 times 6 times 5 divided by 3 times 2 times 1. Let's see. Cancel, 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 cancel. 3 out of 7. Again, if you're running out of time here, you might have guessed that. I have one special element that I'm interested in picking. I'm picking 3 of them, and 3 out of, so it seems like the answer should be 3 out of 7. This confirms it.